We're on day 2 of our 8.8 improper integrals notes, and we're looking at a different kind of issue with our integrals. So the second type of improper integral would be those involving infinite discontinuities. So we said yesterday that usually means vertical asymptotes, or it could just be somewhere there's a hole in the graph or something like that. So that would be contained within the limits of integration. So it's some value that's contained between a and b where there's a discontinuity. So we have to take care of that by splitting the integral into 2 parts. Kind of like we did, where was it? Kind of like we did here for part E, we had to split this into 2 integrals, but we'll be looking to split it at that point of discontinuity. Okay. So you may need to write this in, I guess, if the notes are like yesterday. So sorry if you have to write all this down, but you can pause my video if you need to copy this in. Otherwise, I'm going to go on and just talk about the explanations. All right, so bullet point 1. If f is continuous on the interval a to b, not including b, with an infinite discontinuity at b, then the integral from a to b of f of x dx would be the limit, as we'll make it a c. The limit as c approaches b from the left. That's the important part, because think about this. You're on this interval, right? So here's a, here's b. C is approaching b from the left. We're saying we have some value to the left. Anyway, of f of x dx. And we can turn that around. If the infinite discontinuity is at a, then we'll have to write our limit notation as the limit as c approaches a from the right, because here's c, it's to the right of a, you're approaching from the right, of the integral from c to b of f of x dx. And if you have discontinuities on both ends, with the exception at possibly the c value, so c would be something nice that we pick, then I would have to set up the integral from a to c of f of x dx plus the integral from c to b of f of x dx. And then I would have to follow up with my limit notation for a. So picking something else, like kind of running out of letters here, but the limit as d approaches a from the right. And this might need a separate limit, like the limit as, I don't know, e, maybe not e, f approaches b from the left. So you would, the idea is that you would have limits similar to bullet points 1 and 2 if you had to split this into 2 integrals. Similar to what we did yesterday, just different points of contention. We don't have infinity anymore as our limits of integration for today's problems. So just like yesterday, the integral will converge or come to a finite area if this limit actually exists. So if we can take the limit of this integral and get a numerical answer, then we can say that our integral, our area, converges down to a single value finite area. If we get infinity or negative infinity, then it means that this area is not finite, it's infinite, and so we say the integral diverges. So that is not new from yesterday. For this third part, it could work out that one integral converges. Maybe this integral comes out to like 1/2, but this one goes out to infinity. 1/2 plus infinity is infinity. So if either part of this split up integral diverges, then the whole thing has to diverge as well. Okay, so let's get into some of these problems. The first thing you need to figure out is checking the integral limits of notation. Since I don't see any infinities, my next thing to check is, do I have an infinite discontinuity? So here, x can't equal 0. This is the problem. So on this interval, we would be approaching 0 from the left, right? Because we're coming down on it. Or, I'm sorry, we would be approaching 0 from the right because we're coming down on it. 0 is to the left of our value. So my limit notation would be the limit as, I'm just going to use a because I have a number here, as a approaches 0. Again, we'd be to the right of 0 coming at it, so from the right, of the integral from a to 1 of x to the, I'm going to write it as x to the negative 1/3 dx. So I want to figure out what does that equal. Remember, this is not one of our p integrals. None of these are the p integrals from yesterday, those nice quick ones, because remember, they have to go from any constant to infinity, and ours do not do that. Ours are going from a finite number to a finite number. All right. Anyway, so that just means we have to integrate using our normal rules. So this is the limit as a approaches 0 on the right. If I add 1 to negative 1/3, I get 2/3. So x to the 2/3, and then multiplied by 3/2. Evaluate from a to 1. Keeping my limit notation until the very end when I actually do plug in 0 for a. So now I'm going to use fundamental theorem. So plug in 1, you get 3/2. Minus plug in a, you get 3a to the 2/3 over 2. And I can drop the limit notation because now I'm plugging in 0. So this remains 3/2. And then 3 times 0/2 is just plus 0. So 3/2 is my final answer. And just like we said yesterday, that is the answer for the area of the space between this curve and the x-axis between the values 0 and 1. Even though our curve isn't defined at 0, that is the area. In other words, our integral converges, and it converges down to 3/2. All right, let's do the same thing for the next one. So again, 0 is the problem. X can't equal 0. So I'm going to set up kind of the same limit notation I had before. The limit is a approaches 0 from the right, because you would be coming at, it's kind of hard to see, you'd be coming at 0 from the right side. Of the limit from a to 2 of x to the negative 3rd dx. So again, this is not one of those p integrals. It doesn't go up to infinity. So I just integrate using my normal methods. This would become x to the negative 2 over negative 2. So I'll just write that as negative 1/2 x squared. And now I have the limit as a approaches 0 from the right of, if I plug 2 into that, I get negative 1/8. And then minus negative, so plus 1/2a squared. The first term is negative 1/8. Second term plus 1 divided by 0. Remember, that's infinity. We're plugging in something just slightly positive, right? Like 0.000001. Anyway, that would be positive infinity. But the point, whether it's positive or negative infinity, is that this diverges. So this area, even though this is a decreasing function, 1/x cubed, it doesn't decrease fast enough, and so it diverges. If you want more information, by the way, on those, I'm going to try to link together on like what is this idea of why some of these converge and why some diverge. I'm going to find, at some point I had a good YouTube video for that. I'll find it and link it into our notes folder, just if you're curious. Okay, what about this? Let's see. Now, negative 1 and 2 are fine, but x can't equal 0, and that's defined within this interval here. So x can't equal 0. So I need to split this into an integral from negative 1 to 0, and then another integral from 0 to 2. And I'm writing that informally at the top here so that I can save myself a line of writing and just jump right into the limit notation. Remember, x can't equal 0, so I'm going to have to put in a limit for that and a limit for that. Okay, so this is equal to the limit as, since this is my first value is an upper limit, I'm going to make that b. The limit is b approaches 0 from the left, because you would be approaching that value from the left, of the integral from negative 1 to b of x to the negative 3rd dx, plus the limit as a, because now it's the lower limit, approaches 0 from the right, because you'd be coming down on it like that, of the integral from a to 2 of x to the negative 3 dx. All right. Now, we actually, in this last problem, we just did this work. So to keep this video a little bit shorter, I am going to ultimately say that I know this one gets to infinity, so I'm kind of cheating in a way, I guess, on that. but let's just still go through and figure out this part of it. Even though as soon as one part equals infinity, the whole thing equals infinity, but I just want to kind of hammer that home here. So let's go ahead and finish this piece of it. So our antiderivative from the previous problem, -1 over 2x squared, evaluated from -1 to b. Let's plug in the b, -1 over 2b squared. And then if I plug in -1, I'd get minus negative plus 1 over, that's just going to be 2. All right, so this one also is going to come out to infinity, negative infinity, I guess. So negative infinity plus a half plus another infinity. Now, normally infinity minus infinity, that's one of those indeterminate forms. But remember what we said back here. We're just trying to decide, does this integral converge or diverge? So it doesn't matter that I'm getting one of those indeterminate forms in this case. Really, as soon as I show that one of the integrals diverges, then the whole thing has to diverge, whether this came out finite or not. So I was just doing it to see if it came out to converge, but it didn't. Okay, so anyway, therefore, the entire integral diverges. So if you know that one part diverges, maybe this was part B of a free response, and then maybe this is a free response question, you could set this up and make a reference that I know that this term from part B, I know that this diverges, so the whole thing diverges. As long as you write that out and explain it, you'd be okay to do that. All right, what about example D? Let's see, 1 and 4 are fine, but x can't equal 2, and that's contained in this interval. So we need to, again, split it up into an integral from 1 to 2, and then another one from 2 to 4. And we'll use the same process we did before. So the equals the limit as, let's see, b approaches 2 from the left of the integral from 1 to b of dx over x minus 2. In my head, I'm thinking technically, so this is going to become natural log of x minus 2. Do I need a u sub? No, not really, because the derivative of x minus 2 is dx, so there's no extra coefficients I have to put in. Anyway, the other piece is the limit, the limit as a approaches 2 from the right of the integral from a to 4 of dx over x minus 2. Okay, so now we can get our antiderivatives. And like I just said, it's going to be the natural log of the absolute value of x minus 2, evaluated from 1 to b. Same with the other term. It's kind of funny on these. It's not really that, in a lot of the problems, it's not the calculus or the math that's all that hard. It's just all this cumbersome kind of writing that makes it a long problem. Okay, so let's see. One more round of limit notation, because we need to plug in our values for FTC. So this is the natural log of b minus 2 minus the natural log of, this is where the absolute value is important. It's the absolute value of 1 minus 2. So that's not going to be an undefined value. That is the natural log of 1 when you make it an absolute value. Anyway, getting ahead of myself. All right, so let's see. This is going to be the natural log of 2 minus the natural log of a minus 2. All right, now we have natural log of 0. Remember, we can't take the natural log of 0, but if I think about a natural log of x minus 2 graph, or even if I don't really remember about the transformation, if I'm just thinking about a natural log graph in general, that's a bit rough. As you're approaching 2 on the left, I'm not really taking the natural log of 0. I'm really saying what's happening as you get close to 0, or in this case, to the vertical asymptote. So you're approaching negative infinity. So this term is negative infinity. And then this, like I said, is negative natural log of 1 when you take the absolute value, so minus 0 over here, plus natural log of 2. And then same thing here, minus the natural log of, again, we're getting, as we plug into natural log of 0, so as you go towards 0 or the vertical asymptote, whatever graph you're thinking of, you're going to negative infinity. So minus negative infinity is plus infinity. And so again, since either one of these, this converged and this integral converged, I'm not worried about like, oh, I have an infinity minus infinity, that's a determinant. I'm not worried about that. I'm just saying, I think I just said converged, sorry. This diverged and this diverged. And since either one of those integrals diverges, then the whole thing diverges. So therefore, the entire integral diverges. A question I get a lot is like, well, can I just stop? Like, as soon as that first term got to infinity, can't I just be done with it and say the whole thing diverges? I don't have a set answer for that because, like, if you look at scoring guidelines, they always complete the problem. They don't just, like, stop after one term. So that's something I'll need to ask about. I've got a few people I know who grade the tests, so I'll get back to you on that. But I guess I would say for now, like, just go ahead and finish those 4 terms. It didn't take long to do. And that way you know you've definitely have done enough work. Okay, for part E, now throwback to yesterday, we can't have this infinity in here, but we also need to check, do we have a discontinuity? So also, x can't equal 0, right? Because of that. The other discontinuity is at -1, but that's not in this interval. So I have 2 limits that I'm going to set up. The first one will be, oh, and sorry, we should talk about this problem, shouldn't we? So how are we going to tackle this antiderivative? This one's kind of a weird one. We could try some u sub. Let's do that before we get into all of our limit notation. So what could we let u equal? We could try, I would argue the more complicated thing is square root of x. And then that doesn't really help me with du right now. Let's see. If that's u, then du could be what? 1 over 2 radical x dx. Okay, so how does that help us? Well, let's see. Let's work on this a bit with our solving technique. So if I solve for dx, that would put me at u. I've still got this x plus 1, and then this dx is 2 radical x du, right? Doing some substitution. But I can do a bit more substitution, can't I? Because I can say, well, this 2 radical x du, radical x is u, right? So now I'm really kind of going off the rails going into this. So u over u times, what about x plus 1? Well, if u is square root of x, we haven't really had to do this before, but I could say u squared is x. So instead of x plus 1, I could make that u squared plus 1. And, oh, sorry, there's a du in here. And, yeah, it's still an integral. Details, details. Now, this is a really crazy u sub, but if you look at what I have right now, these u's are going to cancel. And then some magic happens because we have 2 over the sum of 2 perfect squares, and that should be kind of jumping out at us. A constant over an x squared, or a u squared in this case, plus 1. That's arctangent. Okay, so I kind of just did off to the side a bunch of the work for the problem. So let's kind of make it formal using our limit notation. I'm I'm not going to make you rewrite all of this stuff, but I am going to rewrite this integral here. So what do we have? We have the limit as, start with the bottom, a approaches 0 on the right, from the right, I should say, of the integral from a to, let's see, this is going to be an arctangent, right? I can't have infinity up here. I need to split this off somewhere. This is going to be the arctangent of u over a. So what, square root of x over 1? What would be a nice value to put in there? We could put in, I suppose we could put in 1 again, right? Like we did yesterday. So we get pi over 4. We can't put in 0. That would be another nice one. But remember, 0 is a value that we're trying to get rid of. It's also not in the middle of the interval. So let's go ahead and split this at 1. All right. Anyway, from a to 1. Not sure how all that writing got on there. And what's my integral again? Let's, we've already done all this. So let's write it in terms of u. It's 2 over u squared plus 1 du. All right, and then add to that the limit as, not a, the limit as b approaches infinity, and you don't need a from the left or the right. If you're approaching infinity, you're coming at it from the left by default, of the integral from 1 to b of 2 over u squared plus 1 du. Keep the limit notation, but go ahead and integrate. So this 2 is out in front. Normally, the integral of arctangent is 1 over a, but a is 1. I didn't write that down anywhere, but a is 1. So 2 over 1, fine. Arctangent of u over a. U is square root of x, and a is 1, so square root of x. Evaluate that from a to 1, and then add to that the limit as b approaches infinity of 2 arctangent square root of x, evaluate from 1 to b. Keep that limit notation in there and sub in your values. 2 arctangent of 1, square root of 1, minus 2 arctangent square root of a, plus, I'm going to run out of room. Now, luckily, I'm doing this on a computer, so I apologize if you just ran out of room. With your pencil, you can kind of squeeze it in. I can give myself this little adjustment. It sort of worked anyway. Okay, anyway, some things didn't carry along, did they? Ah. All right, the limit as b approaches infinity of 2 arctangent square root of b minus 2 arctangent square root of 1. We can get rid of our limit notation and just figure out these values. So 2 times pi over 4 is pi over 2 minus 2 times arctangent of 0. Arctangent of 0 is 0, so minus 0. And then I've got plus 2 times arctangent of infinity. I'm going to write down what those were. 2 times pi over 2 will be plus pi. And then finally, we've got minus 2 times pi over 4, so minus pi over 2. So the pi over 2's cancel out. This whole thing gets to pi, therefore, the integral converges. And remember, converges just means it approaches a finite area. We get a finite area instead of one that just continues to accumulate. All right, application problem. Use the formula for arc length to show the circumference of the circle x squared plus y squared equals 1 is 2 pi. So we want to use our arc length formula. First of all, we need to remember what the heck the arc length formula is. S equals the integral from a to b of the square root of 1 plus y prime squared dx, right? So to be able to use my arc length formula, I should probably solve this equation for y. Y equals 1 minus x squared, square root of that. So let's see. Square root of 1 minus x squared. Think about what we're looking at on the circle here. That's the top half of the circle, right? The y values that are positive, that's the top half. So if we could find the arc length for the top half, we should be able to double it for the bottom half. All right, so let's see how that goes. So let's figure out y prime. Y prime, since this is Since this is 1 minus x squared to the 1/2 power, I'm using the power rule first. So 1/2 times 1 minus x squared to the negative 1/2. Don't forget chain rule. The derivative of 1 minus x squared is minus 2x. So I'm going to clean that up. 1/2 times negative 2x is negative x. And then instead of a negative exponent, I'll write over the square root of 1 minus x squared. All right, and then for the formula, I'm supposed to square y prime. Okay, so let's see. So we have y prime squared is now positive x squared over 1 minus x squared. So I've got this piece of it. What about a and b? What are a and b? We're going from negative, let's see, for x values, right? Everything's in terms of x. This x value, since the radius is 1, this x value would be negative 1. This one would be positive 1. All right, so I could do the arc length is the integral, this is again just for the half of the circle, the integral from negative 1 to 1 of the square root of 1 plus x squared over 1 minus x squared, all of that's underneath the square root, dx, right? 1 plus y prime squared dx. And then if you remember this, we get a common denominator. So we would make 1 minus x squared plus x squared is just 1 over the common denominator, 1 minus x squared. Okay, and then that simplifies a little bit further. So this is really just 1 over the square root of 1 minus x squared. This one should be jumping out at you too, because this is arc sine, right? A constant over the square root of the difference of two squares. They're not always perfect squares, by the way, but they usually are. Like this would still be arc sine if this were square root of 5 minus x squared. That's what I'm trying to say. Okay, so we know it's going to be arc sine. Where are the discontinuities here? 0 is okay, but we can't plug in either of the endpoints. You can't plug in negative 1. You can't plug in 1. So that just means we'll need limit notation on the outside. So this is equal to, actually I'm going to do it over here. It's equal to the limit, actually, sorry. Just to make sure I have enough room, I'm going to bring this work up here. So now I have the limit as a approaches negative 1 from the right of the integral from a to, let's pick a good splitting point. Wouldn't 0 make sense to split it up? Because arc sine of 0 is easy to plug in, right? Arc sine of x, that'll be a nice easy number to plug in. So from a to 0, of 1 over square root of 1 minus x squared dx, plus the limit as b approaches 1 from the left of the integral from 0 to b of 1 over square root of 1 minus x squared dx. Next step is to take the integral or get the antiderivative. No u sub was needed here because u is just x, du is just dx. So this is just straight arc sine of x evaluated from a to 0 plus the limit as b approaches 1 on the left from, oops, my my integral again. Sorry. Of arc sine of x evaluated from 0 to b. One more round of limit notation. Arc sine of 0 minus arc sine of a plus the limit as b approaches 1 from the left of arc sine of b minus arc sine of 0. Finally, now remember this is S. This isn't our final answer, but I can drop my limit notation and say arc sine of 0 is 0. What's the minus the arc sine of a? Now for a, I'm plugging in -1. So minus the, remember, we don't have 3 pi over 2 for arc sine. We have negative pi over 2. Minus negative pi over 2, because the sine of negative pi over 2 gives you that -1 value. Okay, so really that's positive. And then plus, when I do arc sine of b, arc sine of 1 is positive pi over 2, minus 0 again. So the top half of the circle is pi over 2 plus pi over 2, which is just pi. That's the top half of the circle. The entire circumference of the circle is equal to 2 times s, which would be 2 times pi. Now, that's not the only way to show that application. I could have done a quarter of the circle. I could have done an arc length from 0 to 1 so that I wouldn't have had to do this double integral. I guess that might have been easier integration-wise. And then instead of just doubling my answer, I could have multiplied it by 4, and I should get the same thing. All right, so that's it for today. The homework assignment for tonight is homework number 7, which is also posted into Schoology. So please be sure to check that. And then we will come back on Thursday and we'll go over homework 7 and any questions you had from the notes. Have a good day.